All right, today we are talking about capacitors. Let's say you have the two metal plates. You bring them close together but not touching. And then you take your power supply or your battery and you hook it up to the metal plates. By the way, I'm going to use red for positive and black for negative, and I go like this. Doink, touch them together. So what's true about these plates now?
They're charged.
They're charged up. So this one's charged positive and that one's charged negative. If I hold it here, will it keep on charging up forever and ever and ever and ever?
No, there will be.
Why not?
They can only hold so much charge.
Well, actually, it's governed by
How much output?
the voltage difference provided by this power supply, right? So if I set this at 12 volts and I plug my leads into my capacitor, what's the voltage difference going to be across the capacitor?
12 volts.
12 volts. If I set the power supply at 4 volts, what's the voltage difference going to be across the capacitor?
4 volts.
So however much charge they need to accumulate to become a 4-volt difference from one side to the other. Now if I want to put more charge on here, what do? Crank it up to 12 volts. And if I do 12 volts, it's going to put more charge on there. What if I did 1,000 volts? Then I'd have 1,000 volts worth of charge on there.
At a certain point when it jumps
It just
through
starts
the air.
Yep.
Yeah.
Yep. If you try to charge this up to like 50,000 volts or so, guess what's going to happen?
So you see sparks. 'Cause
Yeah,
it's
you're going to be
flying
like, these plates aren't going to contain it anymore. They're just going to jump the gap.
Yeah.
All right, that's called dielectric breakdown. All right, and it's
Is that what
typically,
Jacob Ladder- is that what Jacob
yeah,
does too?
that's what a Jacob ladder or Van de Graaff generator does too, right? All right, so a couple basic fundamental physics ideas. First of all, we know that if the plates were infinite, you would have a uniform electric field between them, right? All right, and also, if you have a uniform field, that means the slope of the voltage graph is constant, right? And in last year, that would have taken the form, the electric field equals negative delta V over D. All right, you probably saw it as VED, right? Yeah, it's the same thing. All right, so if we use a certain voltage difference, the field is stronger when the plates are closer together. If we use a certain voltage difference, the field is stronger when the plates are closer together. That's interesting. You ready for this? Here we go. I'm going to take my power supply, hook it up to my capacitor. I'm actually going to clip them on this time so I can move stuff around and they'll stay clipped. Hook it up to my capacitor. I'm going to put this on 12 volts. And I'm going to pull these plates further apart.
Okay.
What happened to the field strength?
Just-
Yeah, pretend they're infinite plates, sure.
Okay. The E field got the same.
No, the E field.
The E field just got weak. How come?
What?
Because the charge per distance changed.
Right.
Oh,
The
wait.
voltage difference is the same, it's still 12 volts, but since the distance got big, that means the slope got small.
That makes sense.
Why is voltage sensitive?
Because it's still hooked up to the power supply.
Yeah.
'Cause if
This
you-
is forcing,
you
this power
disconnected
supply
it.
is forcing 12 volts. Sorry, I should plug this. There, now it's plugged in.
Hey,
See? Okay.
Oh wow.
so hold on, if
So
you had
convincing.
that graph, see how that graph goes up to the top?
Through the
Imagine
magic
if your
of
D
make-believe.
doubled, but your V stayed the exact same point at the top, your slope would, yeah.
Does that make sense? So, no matter what I do with the distance, since it's hooked up to the power supply, the power supply is going to force it to be 12 volts no matter what. Now, 12 volts spread far apart means a smaller field. 12 volts closer together means a stronger field.
I didn't know that.
My hand would be in that electric field. That's what would happen.
Nothing
You wouldn't get
charge.
shocked because there's not enough voltage at 12
No.
volts.
We're going to talk about sticking stuff between the plates here in a few minutes.
Okay.
All right? But yeah, that's a good question. So does everybody have that basic idea?
Yes.
So let's scroll down a little bit. The ability to hold charge at a given voltage is something called capacitance. All right, the ability to hold charge at a given voltage is called capacitance. And the definition of capacitance is how much charge you can hold for a given voltage. Like, let's say I put 12 volts across these plates, but the plates were really, really big. How much charge could I hold? A lot. What if I had very tiny plates and I put 12 volts across it? How much charge could I hold? Not very much. So capacitance is your ability to store the charge on the plates. All right? So the more charge you can hold for a given voltage, the more capacitance you have. Sound good?
Mm.
Think of it like capacity to hold charge. All right. And that's the definition of it. Anyone know the units of capacitance? The farad, right. Named after Faraday?
Yep.
A farad has to be the unit, whatever the unit, what's the units of charge? Coulombs per volt. All right. So 1 farad is 1 coulomb per volt. Now, here's an interesting idea. Does a capacitor have to use parallel plates?
No.
Actually, not at all. In fact,
Yeah.
in one hand I have a paper clip, and in the other hand I have a pair of scissors. They both have metal in them, right?
Yeah.
Guess what happens? If I bring them close together, guess what I have? A capacitor. If I were to hook a wire up, the power supply up to one and power supply up to the other, and then disconnect it, I could store charge by virtue of the fact that I've got these two pieces of metal close together but not touching.
Are batteries capacitors?
Batteries are
Recharge-
not considered capacitors.
Rechargeable batteries are capacitors,
No.
aren't they? 'Cause-
No, they are not. A battery, by definition, pushes charges from one side of the battery to the other.
But isn't it impossible to
Capacitors, by
recharge
definition,
batteries?
do not do that.
But isn't it impossible to charge batteries? Can't you only, like, once batteries are spent, you can't recharge them? Capacitors.
Let's
you
talk
can
about
recharge.
batteries on a different day,
Okay.
because we're going to talk about batteries when we get to circuits, and,
Okay.
and I'm going to explain exactly how a
that was.
battery does what a battery does.
What's a capacitor good for?
Ah,
Storing charge.
Storing charge.
now I've got this charge all stored up. What can I do with it? I can run around the room, and then I can run back, and then I can go, here, touch my capacitor, and what happens?
So it's a battery.
It's just like it functions
yes.
It
just like a
stores
battery.
charge
It
like a
stores charge just like a battery would store charge.
Isn't it like
Advantage of a
release?
capacitor,
Fast
though,
release, yeah.
is it? Yeah, exactly. Fast release.
Isn't it like all one blow?
Yeah, it can discharge all of its stored energy in as long as it takes for the current to flow from here to there,
Like picture.
like nanosecond.
No, so the batteries control it.
Yeah,
Yes.
battery is a slow release.
So battery would be like if I'm poking Trina, and a capacitor would be just like if I just punched her.
Pushing versus punching, right?
Yeah.
Well,
Yeah.
I was said poke.
Yeah, poking. All right, so here we go. Does a capacitor have to use parallel plates? No. Parallel plates work great, but you could use any two pieces of metal just as long as they're not touching each other. Because what happens if these pieces of metal touch?
Then
They discharge.
Then you don't have a capacitor anymore because there's no more charge left,
Just have one.
right?
Yeah.
They just neutralized each other.
Do you
Okay,
need
s-
contacts?
What's that?
Can you just keep it high
By definition, a capacitor has a positive side and a negative side, or a high voltage side and a low voltage side. Yes, good question. All right, parallel plate capacitors. If you are using a capacitor that is made up of two parallel plates, then the following is true. Wait, what did I just say?
Only if with parallel plates.
Parallel plates.
This equation can only be used for parallel plates. Got it?
Yeah.
What if you have An inner sphere and an outer sphere. Can you use this equation?
No.
No. What if you have a ball shaped like this and a pair of scissors? Can you use this equation?
No.
No. This only works for parallel plates. What's the equation? I think you saw it last year. For parallel plates only, the following is true. The capacitance can be found to be equal to some value kappa, which is a constant, times epsilon naught, which you already know what that is, times the area divided by the distance. What the heck does that mean? Parallel plates. What's the area? The area of the plates.
Of the plates like combined or just one plate?
One plate.
Okay.
One plate. Because it should be symmetrical. Right? What's D?
The distance between them.
Distance between the plates. What's epsilon naught?
A constant.
Epsilon naught. It's the same one you used before. And what's kappa?
A constant,
It's a
depending on
constant. The dielectric.
The dielectric constant. It depends on what is in between those plates. And this is back to Soham's question. What happens if you stick your hand in between? It turns out the capacitor becomes better.
What?
You can store more charge if you stick your hand in between the plates. Isn't that crazy? Your capacitance goes up, which means if you have your power supply connected, if you have your power supply connected like this, right? And we hook up our power supply, and then we stick our hand in between, all of a sudden now we can store more charge. Isn't that cool?
Just because there's more area.
It's because of something that you stick in between. Yes.
If you had a square plate and a circle plate, and they were
The
parallel,
effective area would be whatever
They match up.
Whichever
on-
one.
whatever the minimum matching area is.
Okay.
Right. So if you had a square that was the size of this room and a circle this big, then the effective area would be
This circle.
Circle.
the size of the circle.
Okay.
All right. All right. So anyway, yeah, it turns out if you stick stuff in between the plates, it's called a dielectric, or also known as an insulator. Exactly right. Different insulators have different effectivenesses, different dielectric constants. Vacuum, it turns out, has a dielectric constant of 1.0000000 by definition. Right? Air. Is air better or worse than a vacuum?
Slightly better.
Slightly better.
Slightly better. Why?
Because there's
Because
stuff
it's
inside of it.
air actually has stuff versus vacuum, which doesn't. All right. Rubber. If you stuck a strip of rubber in between, it becomes 2.8 times as good. All right. Notice what I have on the list as having the highest dielectric constant.
Water.
Water.
By a lot.
It doesn't-
Ooh.
There's no water here.
Water is one of the best dielectrics you could possibly use, with the exception of one fatal flaw. What is it?
It conduct.
No, actually, pure water
Your water doesn't.
is an extremely effective insulator.
It becomes contaminated easily.
Right. The instant you get something, anything, some rust
See, it starts to
Salt.
turn brown.
or anything dissolved in that water, all
It
of a
has
sudden it
ions.
becomes a conductor.
Because you're sticking. metal
And what
inside
happens if
water.
you have 500 volts across a water-based capacitor, and all of a sudden your water gets some salt or rust?
Short circuits.
It goes and your whole circuit blows up. That's why you don't use water-filled capacitors.
What are the
You
other
theoretically
ones? There's
could,
another
and it would be theoretically a really good idea, except for the fact that the instant some rusting starts happening, because guess what starts happening when you put current with metal electrodes in water? Rust happens instantly.
What happens if you had gold plates?
You could do gold plates.
Tastes like,
I mean, maybe if you did gold plates wrapped in plastic so you could keep the water pure,
yeah.
then maybe, yeah.
So why are you saying that the water doesn't conduct when it's in a pure form? Because it's so polarized.
Ah, interesting. But in order to conduct, we're not talking electronic conduction, we're talking ionic
You
conduction.
need to have some
And
sort
we
of
need to have
particle.
ions,
Oh, wait, yeah.
right? So, You know, just because it's polarized, one side of the atom gets pulled this way, the other side of the atom gets pulled, or the molecule
can't
gets
swim.
equally pulled the other way. Yeah.
There's a dielectric paint, is it
chlorine is
the strength of the insulation, is that what it is?
I'm going to talk about why dielectrics work in here in a second, but here we go. Weird but true demo, and this is something I'd like to do. I don't know if I can. Take a capacitor, charge it up, then disconnect the battery. So we're going to charge up our capacitor, then disconnect the battery. Then, so the amount of charge on this is set right now, right? Say I got to charge a Q on this, or 1 coulomb, or whatever. Then, if you take a piece of plastic and put it in the middle, what happens to the voltage difference?
It increases.
It actually drops. Why?
Your distance drops and your electrical stays.
Okay,
Wait,
so
is this the
here's
cover now?
what's
No.
actually happening. This is why, if you stick something in between, the dielectric constant changes. You ready for this explanation? This is an explanation you all need to know how to do. Here we go. If you stick in a dielectric, the electric field changes. It actually decreases. Here's why. So initially, you don't have any dielectric. The electric field's just charge density divided by epsilon naught, right? But if you stick a dielectric in the middle, what happens in that insulator is the insulator gets the molecules in the insulator get polarized a little bit and flip around. All right, and you can imagine water doing this because water is really polar. That's why it's such a good dielectric. All right, so the positive end of the water molecules goes to the left side, and the negative end of the water molecules goes to the right side, right? So you've got a whole bunch of water molecules in here. Positive end on the left, negative end on the right. Well, if the water molecule itself are all oriented with positive on the left and negative on the right, that means there's going to be an electric field from one side of the water molecule to the other side of the water molecule. Which way does it point?
The opposite.
It points to the right, which counteracts the capacitor's electric field, which points from right to left. And so if you superimpose the capacitor's electric field on top of the water molecule's internal electric field, they start canceling each other. And so you get less electric field. That electric field inside of the water molecules itself is called an induced electric field, which cancels with your original electric field, and therefore the total electric field in between is less. And if the total electric field is less, if you have the same voltage difference, less electric field, and if you have the same electric field, less electric field, less total electric field, same distance, that means the voltage difference is going to drop, and the capacitance. What? No, this is wrong. The voltage difference drops. Capacitance goes up. Yep. Got it?
Yeah, because you.
Yeah, it makes your capacitor better by sticking something in between. All right. And it does that by decreasing the total electric field, which decreases the voltage difference. All right.
Over delta
You
V,
just said
so
capacitance increases.
capacitance should increase.
It
because
should. This is wrong.
You can have a better
C
capacitor
equals
with
Q
lower
over delta V,
capacitance.
so delta
Yeah.
V, when delta V drops, then that
Right.
means that capacitance would increase.
Okay, let's see. Do we have time to do energy? Let's take a look. It's a whole nother page, and we have 2 minutes.
Well,
Oh wait, we know that already.
Yeah, this is all old stuff. I'm going to save the derivation and say, all right, energy is stored in a capacitor. These are, the equation for the energy stored in a capacitor is 1/2 Q squared over C. And you can derive that using integration. All right? But there are different forms of this equation that you need to memorize. 1/2 Q squared over C, 1/2 QV, or 1/2 CV squared. Tonight, I want you to do the practice problems in your packet. That's it. Thank you.